Oh, geez. That's how good they were. I don't know. What do you think about that metal? Nails through concrete. Fairly excited. Was it the Structural Engineering Podcast?
Welcome to this week's episode of the Structural Engineering Podcast. As always, my name is Max.
And I'm Zach.
And this week we're talking seismic again. We've hit this topic a few times, but we had a couple questions come in from a listener, and we want to make sure we're addressing them. We're kind of doing a little bit of an intro to seismic design. I know there might be a few people out there studying for the SE exam coming up in 2-ish months here. So this is intro to seismic for those that are more on the wind side of things.
Give everyone a good insight on high seismic design and really seismic design in general. So
yeah, I mean it's a lot to cover, but we're gonna try and do the best 30-minute version of it we possibly can. Before we get there, I think we got some news. What do you got?
Yeah, so this absolutely blew my mind, and it is in China. So with the coronavirus going around and everything, they've needed this ability to have more hospital beds, or turns out a whole new hospital, and they have built 645,000 square feet in 10 days, Max.
Jeez.
With modularized construction or modular construction.
All on real foundations, I believe, right?
From what I was looking at, it looks like it's all like very thick, like more or less a mat slab. It seems like it was a big poured foundation or a big poured slab.
Yeah, man, it's wild. It's a 2-story building, absolutely gigantic. I mean, I want to know more about how this building works. Is it to code, or is it a temporary structure?
I'm there with you. I mean, this size of a building would take years and years and years in the U.S. to build. I mean, 645,000 square feet. I mean, it's a massive building.
Yeah, so, and I assume that these modular units were around somewhere, sitting, waiting. So that's helpful, but that's nuts. 10 days. I mean, I wonder how many beds this thing is.
There's 2 hospitals. One's 1,000 beds and one's 1,600 beds. Which is absolutely mind-boggling. I would say the best way to describe the construction, other than having, I believe they said they had over 7,000. They had over 7,000 tradesmen a day on the project, working 24/7. The best way to describe it, it's definitely some sort of a concrete foundation, like you talked of. And looking at the pictures, it more or less looks like very fancy shipping containers, more or less. The way the connections are and stuff is fairly similar.
Yeah, man, I really love modular design. So I think this is a really fun, extreme example of when things can go well with modular. And I don't know, maybe it'll inform some more modular design in the future that maybe doesn't take 10 days. But, if you could do this in 10 days, what can you do in a month or 2 months or something?
Right, absolutely. And this isn't the first time China's done this. They've built a tower in 1 month, and I believe it was over 20 stories tall.
Wow. Just for the fun of it?
Just for the fun of it. Yeah, absolutely. You guys will have to wait for our next episode, and we'll discuss that building a little bit more in depth. But this is, right off the press right here with this new hospital in China, and it's just mind-boggling. So,
man,
Max, let's move on to the tip of the week. What do you got for us?
For the tip of this week, it's a little different. It's not really a tip, but this is a product that I saw in the Constructor or something, one of these construction magazines, and it was something that I didn't totally believe. And you had heard of something like this, but there is a product that is polyisocyanurate foam. So it's rigid board insulation glued to an OSB or a plywood panel. And I've seen this before, and I never thought that it could possibly be used with shear values. I know for, if you're trying to really seal up the thermal envelope of a building, it's not uncommon to put up your stud wall, put up your sheathing on your outside, and then put rigid foam board over the whole face of that, right? A total extra step, I guess. So I read about this in the magazine, and it is rated for seismic and wind shear loads through 1 inch and 2 inches of rigid board foam. And that just blew my mind. I got to talk with somebody at the company, and they sent out a sample, and it's this really cool stuff. And I just had no idea that this existed. it's not something that we would spec structurally necessarily, but I think it's something that it's worth knowing that the option is there. If the architect is pushing for a really efficient thermal envelope, knowing that you can still get an R of 6.5 with this. It is just like a regular wood shear wall, more or less. I think the values are a little bit lower, but through slightly longer nails, you just punch right through that foam and you apparently get the same value. So I don't know. I was very surprised. The guy I talked to sent me the ICC report that I got to read through. So it's the real deal.
When you were telling about this, I was pretty skeptical. In structural engineering, foam isn't really something we design with, right? So when you start putting that on a shear wall, you're like, what the heck?
I know.
It kind of makes sense. It makes sense that it still works because of your failure mode of a plywood shear wall.
Yeah, absolutely. I kept asking the guy when I was on the phone with him, like, but the foam has to be like, the nails aren't going to bend. He's like, I'll just send you the report. I don't know what you're talking about. So that's the tip of the day. This stuff's pretty cool. The company is Hunter. The product is XCINB. I think the NB has something to do with nail board, but
interesting. Now we're real quick before we go into our topic for the day. Where would you see this being used? What type of construction?
This would be commercial. So this is like type 5 commercial is what it's approved for.
Okay. The only other time I've kind of seen this was in residential construction where there's OSB and then it was backed with like a 1/2 inch or an inch of kind of a rigid insulation of some sort and then up against the studs. So interesting.
Yeah, that was cool stuff.
All right. Well, thanks, Max, for teaching me even about that stuff. It's really interesting. Let's dive into the topic for this week.
Yes. All right. So where shall we start with this? Right. I think from the beginning we can discuss codes really briefly. What type of codes that we have to look for seismic design? Like what are we looking into for our loads, for our criteria? We've hit this one many times, but I don't know. What do you think, Zach?
Well, Max, for codes, it's a great question. We always start with IBC for everything more or less that we do, and then take a directive from there. The IBC does have provisions to go through seismic design to an extent, but I would jump right to ASC 7. And that's the codes that kind of get you your values of loading for your material. We'll go into that, but then there's also codes per your material. So there's a masonry code that goes through, special masonry shear walls. The ACI goes through moment frames and concrete shear walls, concrete moment frames. You have the steel seismic design guide. Even wood has the special provisions of wind and seismic. So within the material and within those different standards, they have the information needed to design that system. But for this conversation, I think we should more talk about ASC 7 and kind of really go through the limitations, what's in there, and kind of the step-by-step, so that any of our good friends out there that don't work a lot in high seismic have a good understanding of what to think about, what to, let's say they get a project and they're trying to help the architect lay out kind of lateral elements for those moment frames, shear walls, brace frames. And I think that's something that can really help. Our chat here could really help drive that conversation.
And you mentioned, obviously, so ASC 7 is where we're going to be living for this one. A massive portion of this book is dedicated to seismic, from chapter 11 all the way to chapter 23. So to cover all this in our 30 minutes isn't going to happen, but most of our focus is going to be on chapter 12. That one would be seismic design requirements for building structures. We do have a episode which kind of covered a lot of chapter 11. It's one of our early ones. I think it still holds up. The recording quality was maybe lower, but if you flip back to one of our first episodes, if you're interested in basics of seismic design, basics of seismology, really, chapter 11 gives us a lot more there, and we're just going to skip that for now.
That sounds good, Max. Now, to start off talking about high seismic, for maybe our listeners that don't work in it often, where is high seismic in the United States? What regions?
Well, we got our obvious one, right, which is the West Coast. Everyone thinks seismic California. California has very high seismicity. It has some of the highest accelerations, but my favorite thought is that it is pretty much tied with Northwest Tennessee and Kentucky. You see SS values above 0.75 in both of those areas, which is absolutely nuts. Those are the highest in the country. But then on top of that, we have a couple others. So where I am, Salt Lake City, vertical line right up to Jackson Hole, up into Montana. That's all high seismic territory, not as intense as California or Tennessee, but getting there as well. And then also the far northeast starts to get into some seismicity, but not that strong.
All right. Well, now that we kind of have a good understanding of where seismic occurs in the United States, let's kind of dive into ASC 7, kind of chapter 12 as you discussed. Chapter 12 starts off with kind of choosing a seismic system. Now, Max, when you're sitting down with a client or an architect, what's the discussion like when you're trying to determine the system?
I think for seismic, when you're walking through with an architect, one of the big key elements is continuity in your lateral system, having a favorable geometric layout that doesn't have a lot of these big bump outs. There's things called horizontal irregularities, vertical irregularities. So the more boring your building looks, the better it's going to be for seismic generally. That's not what the architect wants to hear, and that's not how it ends up being. You can do all sorts of creative stuff, but when you're kind of laying out a system with the like an overall shape of your building, the less extrusions, weird corners, tends to be the easier design, but we can get around all of these things. What other things do you think of when talking to an architect?
One big one I think of is, to me, there's three really, the three main systems to resolve lateral forces, and that's a brace frame, a moment frame, and a shear wall. And more or less, we can do that for any structure. We can go to a whole nother level of using damping. We could use base isolation, but those systems still require some sort of lateral resistance. To me, sitting down with the architect and understanding kind of the architectural features of the building, do we have a lot of areas that have solid walls? Kind of the construction type of the structure. Is it steel? Is it concrete? Is it wood? Is it masonry? Those will start driving the systems that you're looking at. So let's say it's a steel building. The architect wants to have the ability to renovate, or the owner wants to have ability in the future to renovate the building and move things around. And they also want a lot of windows. Well, that to me instantly says moment frames. Okay. And then you kind of work through that route. Moment frames have their own issues as they're super flexible. And when you're trying to figure out, your drifts, that can be challenging. And then on the other hand, the brace frames, if you can hide them in good locations, if the architect's okay with exposing them, then that's another great option to go. Brace frames are about a third of the cost of moment frames, so they're definitely a good option to go with. And this is in very general terms. Once you get to the eccentric brace frames, these links, and there's a lot of systems out there that can add some more cost to your building, but are very beneficial. And then the last one is your shear wall element, whether that be wood, masonry, concrete.
What would you say? Looking at these three systems sort of generically, what is the negatives of some of these? Because you had mentioned, moment frame kind of has its own problems. If you were to break them down like positive negatives of the generic systems, what would they be?
Oh, absolutely. So moment frames are the quickest and easiest one to determine. You're going to either need to fix the base or you're going to have huge columns to mitigate drift. And in seismic, there is drift limitations for structures that you have to meet. And so the higher your building gets, the more it's trying to drift. And brace frames, the real issue in brace frames is trying to keep them out of the architectural areas that don't want to be seen. They don't drift really much at all. They're very stiff elements. They drift more than a solid wall drifts, but they're in the steel world, they're a lot easier to deal with.
So with the moment frames, I did want to mention, it doesn't, exclude you from a lot of things. We talked with the guys at Side Plate, Ryan over there a little while ago, and they have a 22-story side plate, a moment frame building. So even though it's more flexible, you can still do some pretty impressive stuff with it. You're just more likely to be limited by the deflection versus in a brace frame, you're probably limited by your strength.
Absolutely. And with your moment frames, you're going to see a lot bigger columns. the architects have to work through that than you would with a brace frame, almost every time.
Yeah, and I think each of these, has certain restrictions. If you're looking at a special concrete shear wall in seismic design category D, you have a height restriction of 160. Now, that's pretty darn high, and most of the structures that anyone does generally are less than 160, right? If you look at the stock of buildings in the United States, there are not that many, honestly, over 160 from a percentage standpoint, right? So each system has its own limitations depending on the design category you're in. They kind of come in bands, right? So there's the 35 and 40 foot line, 65 foot line, and then you pretty much jump up to the 100 and 160. There are many that are not permitted in high seismic regions. So I don't even have to look at the table here. If you had a mild reinforced, or what do they call it, a plain concrete shear wall, it's an R of something like a 1.5. You're not using that anywhere in a seismic region. That's a BC kind of system.
Yeah, and there's a lot of different things. Yeah, an RF3 system, right? It's probably something our listeners are very familiar with. Even in non-seismic regions, that's probably the biggest fallback for steel structures. An RF3, not detailed for seismic, and that's something, again, you're not going to really find yourself using that in high seismic. So you're going to be jumping to those intermediate and special detailing items or selections for steel, concrete, masonry, and wood shear walls. So that kind of leads to our next question, Max. How do you determine what level of R to use for your system? Let's say a special versus an intermediate.
Table 12.2.1, of course, right? So all this is very nicely tabulated, and that's how you would get your R, right? With the system that you've decided. It's pretty prescriptive on what system you will end up with. If you are able to do, let's say, depending on your occupancy, where the building is located, the height of it, you're pretty much going to be restricted on what type of system you're even allowed to use. If you're in a high seismic region and you're doing a shorter building, I think in those cases, a lot of people in a high seismic area will still use a higher R value system, and there can be some pretty good benefits to that nonetheless. So pushing your R a little bit higher, though it's generally more detailing and a little more field work. Let's say you're looking at concrete and the rebar is a little more involved, right? Or masonry, and you have to have more vertical and horizontal elements. You do end up with way lower forces. We talked a little bit when we talked with Patrick McManus about the benefits of using higher R systems in lower seismic areas. Doesn't always win out, but when you have high foundation costs, a high R can really pay off. So I don't know, am I actually answering your question at all?
Yeah, no, you absolutely are. And I think the other thing that goes with the R, and this is kind of something I was told when I was working in the Northwest, was kind of choosing that higher R is the better approach to take. The higher R you obviously, the higher the R, the less the force you're designing for. But in those high seismic regions, the detailers are used to it. The fabrication shops are used to it. The installers are used to it. Now, when you start trying to do high seismic detailing in a moderate seismic location, you might start having issues with fabrication shops and installers understanding the limit, what you're trying to achieve, and especially finding fabrication shops to know how to deal with the different types of material, the higher grade, the higher strength, let's say steel you're using, for instance. There's also issues like if you try to use a special masonry shear wall in an area that isn't used to it, the masons aren't used to filling the heck out of that wall with rebar and ties and boundary elements, and so it definitely can become a lot more expensive and get that unknown factor in moderate and low seismic. But in high seismic, I think it's the best route to go. And if you have the ability to use an R of 8 system, I would go with it. Every single time you're going to have less elements, potentially, or less length of elements for the higher R value that you use.
Let's talk for a little bit. I know we said we'd stay in chapter 12, but I think there's a couple things in chapter 11, actually, and one in chapter 20 that's worth mentioning as the intro to seismic things that are really important, because we've already talked a little bit about the seismic design category, and I think a lot of people will sort of know what that means, but let's talk a little bit about how you get there, right? So there are two tables that will give you the information you need. One is based on SDS and one is based on SD1. And really the only thing that pushes you into one seismic design category or another is the occupancy of your building and these short period response acceleration parameters, or 1 second response acceleration parameter. So you've got risk category 1, 2, and 3 buildings all get lumped together, and then 4 have their own column. And you go down the table, and if your SDS is higher than, I don't know, 0.4 or something, you're in D. And then there are a couple exceptions there, and these are like the really big ones that really kind of like only coastal and Tennessee. But if you have an S1 mapped response value greater than 0.75, really big, that's going to bump you into those higher risk seismic design categories E and F. Zach, you want to talk about site class a little bit?
Yeah, so site class, it lives in chapter 20. It's really more similar to chapter 11. Site class is determined by a geotechnical engineer. It's in high seismic. That's like the first thing you're getting from your client is a geotechnical report. It's going to talk about your site class, and site class is really going to affect what your building's doing. And maybe this is a first time you're hearing this, but as seismic waves are moving through the ground, depending on the type of soil that is there, rock or whatnot, it changes the amount of acceleration that's seen at the ground level. And so it's very important to get this understanding of that design, that site class. What you'll typically see is a site class D. In previous editions of ASC 7, you could just assume that. Now you're penalized for doing that. There's some values that we won't get into that have a bound if you just assume a site class of D. But really the best way to go forward with all this is to do the testing, and really it's what the code is now trying to push to do. So
as you said, the site class D used to be able to assume that. That's no longer the case. If you assume that in IBC 18 and on, you get hit with the penalty that's roughly around 20%, 25. I kind of forget what the exact number is. The way they check these things, like you're alluding to, is basically the average speed of the shear wave. So pretty much everything in geotech, they test by dropping something heavy on the ground and seeing what happens. They do that for this as well. They've got two options. They can drop something really heavy and put a boring through the ground and listen to how fast those waves propagate through the ground, or they drop something heavy with something sharp on the end of it and see how deep it goes into the ground. A very soft soil will have much slower shear waves and potential for liquefaction once you get really soft. And a much firmer soil, those have much, much higher shear wave velocities. So those are like your solid rock kind of things.
Yeah, and if you guys want to listen to an episode about a real world kind of talk about site class, we discussed the earthquakes out in California, and they had a really high magnitude of an earthquake event, but it didn't affect the structures as much as they you would have expected with that. And it was due to the site class in that area and the understanding of the geotechnicals information. So when you start getting into the higher seismic stuff, I would say you're at least talking to your geotech once or twice during the project about seismic parameters and kind of understanding those things. The other nice thing, and this doesn't really go for site class, but more the bearing side, is in seismic and in wind, you can increase most of the time your bearing by a 1/3 increase, and it's very beneficial in seismic to get that.
Absolutely. All right, let's jump to how you look at how you analyze the structure for seismic loads. There's two main ways. One we call the ELF method, or equivalent lateral force, and then the dynamic method, or modal analysis. Maybe hit ELF first. What do you think?
So ELF, as I like to call it, is probably where the majority of the U.S. buildings are sitting to a good extent. They're going to be kind of your shorter periods. When you're getting to taller, kind of longer range over over a second period structures, you're going to find going the dynamic route is key. And I'll when I'm done with this, I'll let you talk about how awesome dynamic is. And so, ELF is where you're going to start. You're going to pick your R value. You're going to go through the whole procedure in Chapter 12. I believe Section 8, if I'm remembering that correct off the top of my head. It's the first procedure in the seismic design section to evaluate your building, and is what you're going to use majority of the time. Some keys to remember while doing that is there is different limit states, or not limit states, but different equations to use to find your C sub S to then determine your base shear of your structure. Those are determined off of your response modification factor and could potentially be determined off the period of your structure as well. Once you kind of get through that,
I think it's worth mentioning, so for most of the lower rise structures, one's up to about maybe 4-story, unless you're moment frame, you're going to be using this equation that's just SDS over R, and then I's in there too, but we're just going to assume I's 1 for this whole talk, right? So that CS is going to be a total plateau for your building period, and that's the plateau of our design response spectrum. Once your building period exceeds SDS over SD1, every time I say that, you can just reverse it. SD1 over SDS. You start to decrease in the strength that you're required, or the inertial force of the building. So you're dividing your SD1 value by the period of your building. Most analytical software that we use will just spit out the period of building pretty easily. If you don't do that, if you had to answer this on a pen and paper quiz, you can do the approximate period, T sub A. And that will give you a slightly more conservative, I think slightly lower period structure than you may have realistically. So that's giving you a little more forces than you might actually have. The higher your period gets, the lower the force on your building.
Yeah, and that is a key when looking through the ELF method. When you can get to those taller buildings that are more flexible, you can get that higher limit in there, and then you're on that constant velocity kind of curve when you're looking at that map. You're not at that plateau, and so it really starts dropping down the base shear you're going to use for that structure.
Absolutely. I do also want to mention this really cool portion that you don't get to use that often, but if you're doing 4-story and less, or 5-story and less, pretty square buildings, if you have perimeter frames, so your row is 1, your torsion is low, you can actually take a reduction. So this is 12.813. You get to take a 70% reduction in your SDS, which can be pretty substantial. A lot of times you don't get to use this. It's not that hard to get bumped to a row of 1.3, whether it's an irregularity or eccentricity. If you have a central core building, you probably have some accidental eccentricity, so you're a 1.3, but when you can use it, you should definitely use it.
Absolutely. In seismic, there's so many different factors that can penalize in a sense of your basic load that you get with a rho value, which is a redundancy value, an omega value, it's an overstrength value. And there is so many different reasons you'd have to use one or the other. Never them concurrently, but one or the other is a limiting factor of what you're looking for.
Yeah, and again, for like people taking the SE test, from what I hear, footnotes and these little exceptions make up a pretty substantial part of the questions, the gotchas. So keeping tabs of the exceptions and when you can't do certain systems, things like this are going to be pretty valuable.
So Max, what about this dynamic idea that you discussed a little bit here?
Oh yeah, linear dynamic analysis, sometimes called modal response spectrum analysis. So this is when, this is assume you can do this by some pen and paper method, but I sure haven't. So this is pretty heavy on the computer, but if you're using a RAM or I assume a RISA, it's pretty easy to do, and it can have really large benefits. So when you're looking at the ELF method, you're assuming a first mode approximation of the forces on your building. So that is your building is acting like an inverted pendulum, waving back and forth. The forces are distributed basically opposite of hydrostatic pressure, where it's low at the bottom and it builds to the top. like opposite of a water column, right? But building will actually twist. It might go into a second mode and it'll act differently on the X and the Y axis. So you have all these different modes, right? 3 per floor is, I believe, a reasonable estimate.
Right.
So if you're doing a modal response spectrum, you are looking at how each of those modes, the participating mass, contributes to the overall force of the building. So when you're looking at your design response spectrum, you can see, as that period moves along, your acceleration is different. So in the same way, the different periods of each mode, they will act together, and one might have a lower force because it is a higher period. The other really nice thing about the modal response spectrum is that you're probably not going to have this, your opposite water column looking force graph is the absolute worst thing that you can have for overturning on your foundations. The true response is something where more of your force is central to the middle stories. I'm more used to this 5-6 story building. And so you might see more force on the 4th level kind. And once you're getting up to, 10, 15 stories, it's going to make a huge effect on the size of your foundation. So you absolutely, it's easy enough to do. It will save a lot on foundations, on steel. Ultimately, the bottom brace will be the same with the 716 ASCE7. You have to scale your dynamic to the full force of your ELF. In previous editions, you could go up only 85%. So it's, at the base, your shear is going to be the same, but it's that overturning because the force is applied lower can be really beneficial.
So Max, on that same note, in the ELF method, there is in chapter 10 or 12.10, you can reduce your overturning by 25%. And that can be beneficial as well.
Yeah, you're right. Absolutely.
For our listeners here, it might be a little bit confusing of when should they use the ELF method, when should they kind of use the dynamic method. What would be your tips on that?
I mean, if you're over 2 stories, or over 3 stories, that's my line. If you're over 3 stories, it's easy enough to do the dynamic. Your forces are going to be lower. Where it gets a little confusing is like your diaphragm forces, you have your FPX, you have your ELF that you had to run anyway, you've got your modal now. It's like, which do you end up using? So that's where, unless you have a really good system down just for how you get to the forces that you need, enveloping things in each of these programs is not always as easy as you'd like it to be. So is it worth adding the complexity of a modal analysis to the mix? I think once you're past 3 stories, it probably is.
Okay. That's great to hear. So you brought up some diaphragm forces. We haven't discussed that yet, but there's also in seismic design, you have to design your diaphragm for different limitations. You also have to design your drags and cords and your collectors for different types of overstrength or row factors. And then within chapter 12 as well is where you find your drift limitations.
Heck yeah.
Now the thing, and I think this would be good to kind of hit real quick, is what are the irregularities that are really going to start hurting us, and maybe in a sense of what can I be looking for, and what can I help relay to the architect is not very beneficial to our structure. They can do it, but it's going to hurt.
Yeah, absolutely. So the one that always stands out to me that is a common is soft story irregularity, right? We think of soft stories like, all these photos of houses in California that collapsed. But the ASC7 defines soft story as your first story having a stiffness of 70% of the story above it, or the average of 80% of the 3 above that. Anyway, you could just think about, is your first story fairly softer than the one above? And the reason it may often be is a lot of times architects want this grand first lobby, let's say you're doing office space. You want to walk into a big space. So people will bump that first deck up to, 18 feet or something. And once you're in, who cares what it looks like? So maybe your ceiling height's down to 8 feet. Maybe your deck is 12 or something like that. So you have this immediate drop in your floor to floor height. If you are using a system like a moment frame where maybe it's the same column continuing up, right? Where it's not a brace, you could just bump it up a lot. And the moment frame, the columns carrying a lot of your stiffness, you're potentially pushing that soft story regularity immediately. It's not always a problem, but it's something worth considering. I think some of the other ones that can be problematic, reentrant corner irregularities, or anything that would cause torsional irregularities. So any weird shift in the floor plan of the building could cause this torsion, which that one can definitely add up, getting you to a row of 1-3 very quickly.
Yeah, the one I see often done is where you have a shear wall or some element that stops at one floor and then all of a sudden starts on the other end of the floor. It doesn't continue all the way to the ground. That really dings you. Having that discontinuity of not having your vertical frames go all the way to the foundation, not having your shear walls go all the way to the foundation. And you might say, man, that's weird, but where I see it done most is wood shear walls.
Yep.
And you stop your wood shear wall on your second floor, but you still have to deal with the overturning. And now that overturning needs to be omegaed, and that drag force coming out of it does as well. So, or overstrength, we keep saying omega, same thing, but you really start increasing forces when you're doing that, and that's something that has to be, thought through. It just needs to be known that there's penalties when you start making kind of things and loads jump around. Where again, in seismic, keeping it simple is completely key.
Absolutely. I want to add to what you said with the wood shear wall. I think another kind of common one is moving doors and windows later on in design. If you don't have the same vertical stiffness, say you're down to your lower level and someone says, oh, can we get a door in here? And you're in the shear wall. If your lowest shear wall is less stiff than all the ones above it, that's also very problematic. Or any gap, if you have a balcony coming out or something to interrupt your flow of shear walls vertically, you'll get penalized for that.
Great point. So if you go into chapter 12, there's a whole list of vertical and horizontal irregularities. The ones we discussed are the common ones. They also, in those tables, give you the section, and they kind of explain to you more the penalties that you will occur. One interesting one that I know that happened in a seismic region, I'll just go over real quick. I believe it was in Chile. There was a really tall building, and let's for the sake of the conversation, let's say it's 20 stories. And on the 15th story, they put a bank in, and the bank had a vault in it. So you had this massive irregularity of mass, which is in there. And it caused the building to have like some massive issues that actually failed the structure, because you had this random mass sitting up there that was not working for you. It was working against you. So there's definitely these things when you get to high seismic are very important to understand and to go through.
Yeah. So, Zach, I think that was the fastest we've ever talked in an episode. We're trying to cram a whole lot into 30-ish minutes. I think this one's going to stretch a little bit farther. Before we sign out for the day, I think we had a couple specific questions from a listener, and I feel like we should just hit them real quick and then bow out of here. Let's see. I'll ask them to you. In seismic design, is design time longer?
I don't think so. I think that the 12 week, if you're talking about the same exact building in non-seismic and in high seismic, you're still getting, the same amount of time to do that. I think when times start getting a lot longer is when you're doing a lot bigger projects. I don't think it's dependent on your seismicity.
Yeah. Would you say the fees are bigger for more complex seismic, or let's just say in seismic regions?
Again, I'll use the same reference point. I think if you design a building in a wind governed zone and then you're asked to design the same building in a seismic governed zone, you're not going to be able to do a very good job, from my knowledge, to convince an architect or a client to pay you more money because of that. Technically, you should be reviewing seismic design for every structure to an extent. Anything that is governed by ASC 7, Chapter 12.
Got one more for you to finish it off. How hard is it when you're talking with architects in the beginning to convince them not to do things that are hard for you in the future? So, in a seismic area, let's say the architect wants to do an absolute inverted pendulum. Is it easy to convince them that that's not a great idea?
I found that with architects that work a lot in high seismic, it's a lot more easier to discuss all these things with them. They have a good understanding of kind of the challenges of seismic, especially when they've had issues in the past of having too many braces or walls or elements in the way, and you start telling them and you communicate with them. The biggest key of all engineering and everything in life is communication. Once you communicate with them the issues that this will cause, it's then back into their in their court to determine if it's worth paying the money. And really just comes down to talking with them and going that route. I haven't had the best luck explaining to them that things need to change. I haven't been asked to do anything absolutely wild, but there's definitely been times that I've had to discontinue certain vertical elements. That wasn't fun. Kind of fun. You get to really oversize the heck out of stuff, and they're okay with it. Or not oversize it, but size it per code. So I think it's a interesting conversation with architects and the ones in high seismic know that there has to be something, and that's my favorite part. You sit down with them at a conceptual or a schematic level, and they say, "Okay, where can we put your brace frames?" Or sometimes they'll even have an idea of where to do it. I've had architects say, "Hey, we've got these perfect stair towers. We're going to be concrete. Hey, we've got these great walls, solid walls. Let's put brace frames in them." So you start finding clients that really understand what your needs are to a really good extent. And when they design around lateral needs for you, it just makes the project that much better.
Yeah. And I lied. I've got one more that just popped in my head because I actually heard it recently. This is not one that someone had sent in. This is something I heard in real life. Someone is asking, is this building seismic proof, earthquake proof? What's your comment to that misconception? When, I mean, the question is inevitably asked, "Oh, you designed, it's got BRBs, so it's earthquake proof?"
Yeah, nothing's earthquake proof. I mean, the code does the best for life safety. That's really what it's mitigating for our typical buildings, our risk category 2 structures. I would argue that if you go to a base isolation system, you're pretty much earthquake proof to the best extent. You're limiting the acceleration in your structure. Really the only way possible to be earthquake proof. Come up with some sort of system like that. Otherwise, we design 90+% of buildings in the US to not be occupiable after a major event. So I'd say it's proof in the sense that people will be able to get out and there'll be hopefully no loss of life. But after the event, the building's being rebuilt for the max considered event.
Nice. Now I'm totally done. That was the fastest we've ever gone through an episode, and I think it's going to be a long one, but that's all right. Thank you all for listening. I hope you enjoyed it. If you have any questions, please reach out to us. We got an email down there. We Instagram, all sorts of stuff. So reach out, and hope you have a great day.
Talk to you guys later.